everybody. This is Miss List, and I am here with 4.5, which is on stoichiometry. So, the concept of stoichiometry, that word stoichiometry, comes from a Greek translation that literally means to measure the elements. And the way that we use stoichiometry in chemistry is we use it to switch from moles of a known substance to moles of an unknown substance. And usually that is done via a mole ratio. And so this pass through in this graphic organizer is based on the mole ratio from the balanced chemical equation. So I can switch from my moles of my known substance, which on this graphic is, to moles of my unknown substance, which is moles of B. And that's essentially the idea. If we are not given moles, then on this side, these are all the different ways that we can get to moles depending on what we are given. So if we're given grams, we can get to moles via the molar mass. If we are given particles, we can use Avogadro's number. If we're given PV and T, we can use the ideal gas law. If we're given a volume and it specifically says we're at STP, I can use 22.4 liters. And then if I'm given a molarity or a volume of a solution, I can also get to moles that way. This left side of the graphic is for different ways we can get to moles. Once I have moles, I'm going to use my balanced chemical equation, which is where I would get my mole ratio from, to move from moles of the unknown to moles of the known. Then, of course, on the right-hand side, we can then get to any of these things using the same set of information. So if I want to know how many grams of something would be made from a chemical reaction, then my next step would be to get back to grams of B, and so on and so forth. So the left and right part of the graphic organizer are exactly the same, and the go-between, the middle part that allows us to switch from one substance to another, is the mole ratio from the balanced equation. So let's look at some examples. This set of notes is working through some examples. So on number 1, we have, according to the balanced equation, how many moles of HI would be necessary to produce 2 moles of iodine, starting with 4 moles of KMnO4 and 3 moles of H2SO4. So this is kind of an interesting question because they gave us a lot of information. They tell me that I'm starting with 4 moles of KMnO4 and 3 moles of H2SO4, but they're asking how many moles of HI would be necessary to produce 2.5 moles of iodine. So I'm actually going to start with that 2.5 moles of iodine. And because I'm already in moles, I can go straight to my mole ratio. So this is where my balanced chemical equation comes in. If I look at the coefficient for iodine, it is a 5. And what that means is that 5 moles of iodine would be produced. And so iodine and iodine can cancel. And then they want to know, relative to HI, how much would be needed. So I'm going to put HI in the top, and then I'm going to multiply 2.5 times 10, which is 25, and then divide by 5 in the bottom. So to answer the question, I would need 5 moles of HI. What made this one tricky is they gave us some other numbers, these guys. And when you sift through the problem and see what are they actually asking me, I actually didn't need that information at all. They want to know how many moles of HI would be necessary to produce 2.5 moles of I2. So that's what I need to answer. I'm starting with 2.5 moles of I2. That's what the goal is. That's my known amount. I want to get rid of my I2 on the bottom, so I pull in my balanced chemical equation mole ratio. It's 5 moles of I2 to 10 moles of HI, so that goes in the top. And then we complete the conversion. So that one wasn't really so bad. On number 2, we have solid aluminum reacts with hydrochloric acid to produce aluminum chloride and hydrogen gas via the following reaction. And the first thing they're asking us is to write a net ionic equation. So this is a throwback to when we covered net ionic equations. Remember, you can only break apart my aqueous. So I can break apart hydrochloric acid to make 6 hydrogens and 6 chlorines. And then I can break apart my aluminum to aluminum, and so I'm breaking apart this guy. 2 times 3 would be 6 chlorine. And so remember, we want to cancel what appears on both sides. So in this single replacement reaction, the only thing that would cancel would be the chlorine ion. So I'm going to rewrite what I have left, which would be 2 aluminum solid plus 6 hydrogen ions. And that's going to be aqueous in solution. That's going to produce 2 aluminum in aqueous solution plus 3 H2 gas particles. So now they want to know how many grams of aluminum are necessary to produce 0.5 moles of hydrogen gas at 25 degrees in 1 atmosphere. So again, they've given me some extra information to try and make this a little bit tricky, because I know, first of all, I can use the 22.4 if I'm at STP, and STP is 0 Celsius and 1 ATM. So what that tells me is that this is done at room temperature, but they're giving me how many moles I need. And so I actually don't need the STP information or the temperature and pressure for this. I can go straight to my calculation. 0.5 moles of H2 gas. I can go to my mole ratio. The coefficient on the hydrogen gas was 3, so it's 3 moles of hydrogen gas to 2 moles of aluminum solid. Hydrogen gas cancels, and so it is looking very similar to what we did last time. And then they want me to take it one step further, and they want me to calculate how many grams are necessary. And they give us the mass of aluminum rounded. So moles of aluminum cancel. And the only label that doesn't cancel is going to be the grams of aluminum. So when I go to my calculator, I want to multiply across the top, 0.5 times 2 times 27. And then I'm going to divide by anything in the bottom, which I get 9. Keeping 2 significant figures, I would do 9 grams of aluminum. In this example on number 3, it says, according to the balanced net ionic equation, how many moles of chlorite are needed to react completely with a 0.2 molar KMNO4 solution, and we have 20 milliliters of it. So the first thing I'm going to do is I am going to convert that into moles. And the way that I do that is by multiplying, because the molarity equation is moles per liter. And they give me a molarity. It is 0.2. And I need to know how many moles are in. We do have to change that to liters. 20 mils in liters would be 0.02 liters. And so I'm going to end up multiplying that to get my moles, and I get 0.004. And I'm keeping 2 significant digits, so I'm adding that 0 there. And that is moles of KMNO4, which the K has been canceled as a spectator ion. That's why in our equation, we just see the MnO4 ion. So I'm going to set up my mole ratio now. And it says that there are 4 permanganate ions, so 4 moles permanganate on the bottom. And they want to know how many moles of chlorite are needed. And so the coefficient on chlorite is 3, so that's going to come here into the top, and it's 3 moles of ClO2. So I'm going to take 0.004 times 3 and then divide by 4 in the bottom, and I get 0.003 moles of ClO2 ion needed. Here on number 4, we have a multiple choice question. It says, according to the equation below, how many moles of potassium chlorite must be decomposed to generate 1 liter of gas at standard temperature and pressure. And what they want us to do is to set up what that conversion would look like. Now, because we're at standard temperature and pressure, that means I can use 22.4. 22.4 liters of any gas at STP is going to be equal to 1 mole of that gas. So I can use 22.4 liters only if it specifically says I'm at STP. So one conversion is going to be the 1 mole over 22.4. So all of the problems have that part correct. Now I go to my balanced equation. Remember, this was oxygen, and they want to know how many moles of the potassium chlorate. So I'm going to go to my balanced equation, see that oxygen has a coefficient of 3. So it's going to be 3 moles of oxygen on the bottom and 2 moles of KClO3 on the top. And I want to choose the one that matches that, so I would choose C because it's the one that has the correct conversion factors. Even though they've written them in a different order, we're looking for 1 over 22.4 and then 2 over 3. So C is the only one that matches. On number 5, we have a multi-step problem. The first thing they want us to do is to write a net ionic equation for the reaction above. So remember, we can only break up the aqueous. So I can break up acetic acid into hydrogen and acetate. Number 5 is a multi-step problem, and they still are having us practice our net ionic equations in part A. The first thing I'm going to do is I'm going to separate any of my aqueous. So acetic acid can be separated into hydrogen and the acetate ion, C2H3O2. I cannot break apart anything that's solid, so that has to stay. And then on the right hand side, the only one I can break apart is the sodium with the acetate, C2H3O2. I cannot break apart water because it's liquid, and I can't break apart CO2 because it's a gas. It looks like here the only thing that is able to be canceled is this acetate ion. So I'm going to rewrite what's left over. I have hydrogen ion that's aqueous, and it's reacting with sodium bicarbonate, also known as baking soda, and it is producing sodium ion in solution. It is producing water, and it is producing CO2 gas. Next, they want us to determine the volume of CO2 when 2.5 grams of sodium bicarbonate reacts with 55 mils of acetic acid at STP. Now, on this one, it's actually it's going to be a limiting and excess reactant problem. Whenever we're given 2 materials to start with, so for example, they tell me I have 2.50 grams of this, and then they tell me that my acetic acid is 0.875 molar, and then I have 55 mils of it. So in chemistry, there's this concept called limiting and excess. One of these is going to be limiting, meaning it runs out first, and one of these is going to be an excess. We have to determine which one is going to be our limiting reactant because that is going to limit how much carbon dioxide is produced. So to do that, we first need to convert both of those to moles. So I'm going to start with the sodium bicarbonate, 2.50 grams. I need to put the molar mass of sodium carbonate on the bottom, and that's going to be 1 mole on top. The molar mass of sodium bicarbonate is around 84. Then I want to use my mole ratio, which is 1 to 1. 1 mole of sodium bicarbonate is equivalent to 1 mole of CO2 gas because all of the coefficients in our balanced equation is 1. And I'm going to see how many moles of CO2 can be produced. And I'm going to keep 3 significant digits, and I get 0.0298 for this one. Now I'm going to do the same thing where I have to convert my molarity into A. Now I'm going to do the same thing where I convert my molarity that they give me, 0.875, and I need to know how many moles are present in the 55 mils that we're using, which in liters would be 0.055. So if I do that calculation, I get 0.048, and that's moles of the acetic acid, also known as hydrogen ion. And then this is also a 1-to-1 ratio. So it's going to be 1 mole of hydrogen will produce 1 mole of CO2. And so nothing changes except that my label cancels there. And I get 0.048 moles of CO2. Now from here, I look at which one is producing the larger amount of CO2. The one which reactant is producing the larger amount of CO2. And the one that produces more, which would be this value, if I compare 0.0298 with 0.048, this one is bigger. That means that this reactant that I started with is going to be in excess. The one that makes a smaller amount is telling me that that's going to run out first, and that's my limiting reactant. Now, they're asking in this problem for volume, so I do need to go one more step, and they did tell me it was at STP, so I can go 1 mole of CO2 on the bottom, and 1 mole of any gas at STP is 22.4 liters. So I'm going to take the 0.0298 times 22.4 and get my final answer. I get 0.668 liters of CO2. Now on part C, they are asking us what mass of sodium bicarbonate is required to produce 19 liters of CO2 at 20 degrees and 1.2 atms of pressure. So we are not at STP. If we are not at STP, that means that we need to use the ideal gas law. So they give me a pressure of 1.2. They give me a volume of 19 liters. I need to find moles. The ideal gas law constant is 0.08206. And then 293.15 is what we're going to be in Kelvin. Remember, anytime we're doing a gas, we need to be in Kelvin. So I'm going to divide both sides by R and by the temperature in Kelvin so that N is by itself. So I get N equals 0.947, and technically I should only keep one digit because this 20 degrees, if they wanted me to keep more, they should have written it as 20.0. But since they only wrote it as 20, I should only technically keep one significant digit, which is going to make our math here a little bit weird, but we're going to do the problem as intended. I get 0.9 moles. Now, this is going to be a 1-to-1 ratio. It is 1 mole. I'm not going to go back up to the balanced equation. 1 mole of CO2 to 1 mole of sodium bicarbonate. And then they want me to get this to grams. So 1 mole of sodium bicarbonate is going to be equal to about 84 grams. So I need to take 0.9 times 84. Now my calculator gives me 75.6 grams. Again, this is not going to be very accurate because we really should have had more significant figures up here in our original problem so that we could get a more accurate mass, but we would need about 80 grams if I was keeping to that one significant digit. All right, number 6 says a 5-gram sample of an organic hydrocarbon undergoes combustion and the products are measured. In the reaction, 15.37 grams of carbon dioxide and 7.186 grams of water are produced, assuming the oxygen used for the combustion was in excess. Determine the empirical formula of the hydrocarbon. So this is a throwback all the way to Unit 1, where we're doing the empirical formula. So first, let's think about our chemical reaction. They say it's a hydrocarbon, so that's going to be like CXHY. We don't know what X and Y are. And anytime we have a combustion, it's always going to be plus oxygen gas. And they do tell us that oxygen is in excess. And it says that we make carbon dioxide, and that's 15.37 grams, and 7.186 grams of the water. So first thing I'm going to do is to convert each of those to moles. So I'm going to start with the 15.37 just because that was given to me in the problem. So 15.37 grams, that was for CO2. Now, CO2 has a molar mass of about 44 grams, and that's in 1 mole of CO2. Now, I know that 1 mole of CO2 contains 1 carbon. So that is a 1-to-1 mole ratio. So grams and grams cancel, moles of CO2 and moles of CO2 cancel, and that gives me 0.349 moles of carbon. So now I'm going to do the same thing, but I'm going to do with the water, H2O, because the water is going to give me the hydrogen. So if I had 7.186 grams of water, water has a molar mass of around 18.01 grams, and that's per 1 mole. And then in the formula of water, in 1 mole of water, there would be 2 moles of hydrogen. So grams and grams cancel, moles of H2 and moles of H2 cancel, moles of H2O and moles of H2O cancel. And now I'm going to multiply, and I get 0.798 moles of hydrogen. Now, if you remember back when we did empirical formulas, you want to divide by the lowest amount of moles. So I'm going to divide both these by 3.49. And if I do that, that tells me I have 1 carbon. But if I take 0.798 divided by 3.49, I actually get 2.3 for hydrogen. So for this particular example, we need to have, and anytime we do an empirical formula, we have to have an even number. So I'm going to take both these times 3, which would give me 3 carbons. And if I take 2.3 times 3, that's going to give me around 7 hydrogens. So I would say C3H7 as my final answer. All right, final kind of stoichiometry example. We have a lab scenario. It says a 3-gram sample of magnesium sulfate with X H2O hydrate is thoroughly heated. And then the data is shown there in the table below. The first thing they want us to answer is, why was the test tube heated? Part A says, why was the test tube heated 3 times? And that's to make sure that the mass stops changing. And that shows that the water is completely driven off, completely gone. In part B, they want us to determine the mass of the water in the hydrate. So up here, I'm going to take the mass of the test tube with the hydrate, which is the 27.330, and then I'm going to subtract from it once all the water has been driven off. So I'm going to subtract from it 25.850, and that should give me the mass of just the water. I get 1.48 grams of water. Now, in the next step, they want us to determine what is the number of moles of water to the moles of the anhydrate. So first thing I'm going to do is take my 1.48 grams of water and convert that to moles. The molar mass of water is around 18.01, and I put 1 mole on top. So I go to my calculator and I convert that, and I get 0.0821 moles of water. Then I need to figure out what is the mass of just my anhydrate. This is where I'm going to take the mass of the empty test tube, so mass of the empty test tube, and subtract it from the mass of the hydrate after the 3rd heating. So 25.850 was after the 3rd heating, and if I subtract just the test tube off here, which is 24.310, that should give me just the mass of the anhydrate, which is 1.52 grams. Just like I did previously, I'm going to convert that into moles using the molar mass of the MgSO4, which is 120.366, and that's equivalent to 1 mole. And that gives me 0.0126 moles of MgSO4. So that would be the mole ratio of water to anhydrate. And so that's where my bottom part comes from. I'm going to take my fewest number of moles and divide. So I'm going to take 0.0821 and divide it by 0.0126. And that actually gives me a value that is around 6.5. Now, in real life, when we got a number that was halfway between, we would probably repeat the experiment to make sure that this is an accurate value. But for right now, for us, we're just going to go ahead and round that to 7. So the formula for my hydrate would be MgSO4.7H2O. So this would be a heptahydrate. All right. Thank you for listening. I hope you are enjoying these videos and that you're getting something from them. Please feel free to like, share, and subscribe. I'll see y'all next time.